G'day guys, welcome to lecture 4 of topic 2, uniform circular motion. We're going to start with a theory on this one and do pracs in another video. So here's your learning intention slide. Please complete the KS table down in the bottom corner here. Pause the video while you do this. Alright, now hopefully you picked up that firstly, well, you need to know what is uniform and non-uniform circular motion. I've abbreviated it there just for the sake of keeping things a bit neater. So we need to know what these are. We need to know all these definitions. What is average speed, period, centripetal acceleration, and centripetal force. Average speed we've seen before, so we should be able to clue in on that pretty quickly, but we are going to need to know them how they relate to this topic. And finally, skills. Well, we've got that solved there. Can we solve something about uniform circular motion? So as an emphasis, circular motion, it's only the uniform part that is for the syllabus. Non-uniform would be an extension topic. So when we consider the topic of uniform circular motion, the first thing we should really do is examine the name. Motion's fairly obvious, it's something that's moving, and circular means something that's in a circle, but uniform is the important word here. So why is the topic not just circular motion? Why does this word uniform pop up? Now the word uniform means sameness, okay? And so we need to understand what we mean by uniform. When we are thinking about something in circular motion, it is moving through two dimensions always. If we consider something being spun around our head horizontally, in this case a child with a plane, we can see that it's moving through the x and the y dimensions. So we might say that this is our x dimension, this could be north to south, and this could be our y dimension. In this case could be east to west. I know we normally have x on the east-west axis, but it really doesn't matter. It's all just convention. So we can see here the motion of this plane, it's just going through the x dimension, and then through the y dimension, and then back through the x, and then through the y, and this continues around like this. But it's not going in the z dimension. It's not going up this way or down that way. So the z, which would be the up and the down. Okay, so this is horizontal motion. Now we could certainly tilt it a little bit so that it's going a bit up and down as well. That would be reasonably complex. We tend to treat it in one of two ways, either horizontal and vertical, just because it makes the math a bit easy to start off with. So let's have a look at what would look like in a vertical motion then. So if we consider a stunt bike rider who is going through a loop-to-loop here, we can see that it is going in this up and down direction. Obviously gravity is down here, so we would say this would be our z dimension. And here we have another one. It could be x or it could be y. We'll just call it forwards and backwards for the moment. But we can see, again, it's going through two dimensions of movement here, okay? So one of these is uniform, and one of these is not uniform. And when we look at the forces in a minute, we'll come back to these pictures to explain why one of these is uniform and why one is not. So when we talk about uniform circular motion, we need the following two principles. One, the magnitude of the velocity is not changing. The direction will change because it's going around a circle, but the magnitude will not change. Okay. Secondly, we need to consider that the motion is perpendicular to gravity. So this means horizontal movement only. If there is any vertical movement, then the motion is no longer perpendicular to gravity, and we have to think about what gravity is doing at every point in the circle, or at least some of the major points. And that sucks. Okay, you don't want to deal with that, trust me. You can deal with it on vertical motion, but it does require more complexity, which is why it's not really in the syllabus anymore. So if we look at two instances for circular motion, and here I have a picture of it, we can see that this velocity here at point A and this velocity here at point B, they do have the same magnitude. Okay, this picture is in the text. Feel free to grab your ruler, measure that, and see if I'm telling you the truth. Well, hopefully that the author is telling us the truth. They have the same size. This is principle one. Remember, size represents magnitude, but they do have a different direction. Now, remember, we talked about this before, and there was a question about this in the topic 1 Check Your Learning questions. If there is a change in direction, there has to be an acceleration. Acceleration is any change in velocity. Magnitude might be the same, okay, or at least the final magnitude might be the same, but the direction is changing, so therefore there must be acceleration. All of this velocity in the y direction has been turned to 0, and then it's all been turned into x velocity. So there are some changes happening there. Okay? So we call this centripetal acceleration. Okay, and I'm going to label that on my picture up there. So this arrow here can represent centripetal acceleration. Centripetal means center seeking. Please don't pronounce it as centripetal, it's centripetal. Right. So centripetal in this case means center seeking, that it is being pulled in towards the center. Okay. Now there is a formula for it, of course. It is different though to the acceleration formula we have for linear motion, so it's no longer just change in v over t, because we no longer have our v only changing in one dimension, it's changing in 2 dimensions. So we need a different formula. There is a proof for it. The proof is not part of the syllabus. It involves some work with similar triangles, but I will try to find a good copy of it and I'll put it on eLearn for us to use. Okay. So let's have a look at centripetal acceleration. The formula for centripetal acceleration, we're going to use this diagram. Okay, and I've labelled 2 things. One is the velocity, and we can see the velocity here that I care about is this right angle velocity. We call this the tangential velocity. Okay. The second bit is the radius, and the radius is just the distance from the centre of the circle to the path of the circle. So that's pretty straightforward. Okay. The formula looks like this. Centripetal acceleration, AC, equals v squared, this v, divided by r. Now this formula will be provided to you on your exam book. Nice and straightforward. For centripetal force, because we have an acceleration, there must be a force. Newton's second law still applies. So Newton's second law is F net equals ma. If we change that a, we can then get that F net will equal mv squared over r. Now this is the way that it's written on the formula book. Okay, be really careful with recognizing this. This is under the gravity and motion heading. If you look at this and go, oh, to sum up the forces on my object, I just need to use this formula, and you don't have an r, you might make up, go, oh, r kind of means distance. This will not do anything or anything relevant on linear motion. Okay, so you have to be really careful with these equations, that you don't use the wrong equation for the wrong what's what I'm looking for? The wrong context. I had one student who worked out trying to work out power on a question where they used the momentum equation, and so they worked out P equals m times V when they were meant to work out power for voltage, and I can't even remember where on earth they got a what's what I'm looking for, where on earth they got a mass for their voltage. I think they used the mass of an electron, so it made no sense, their answer. Some other text that we see, this will be written as FC equals mv squared over r, in that the C is for centripetal force. Okay. Let's have a look at the diagram again. So here's our diagram from before. We would be able to put our FC on this, so this would represent either our acceleration or our force. This would also be our force. Now these would have the same magnitude, okay, but they would have different directions because, well, the center is in a different spot relative to the motion of this object here. Right. Let's have a look at. Let's imagine that this is our plane from before. So if this is our plane from before and we are looking down onto the person, and our centripetal force is acting inwards here, that means our force of gravity must be acting down, and that's the symbol we use for down into the paper. It's meant to represent the bottom end of an arrow going down. Thing is, arrows only have 3 flights on it. They don't have 4. This is to represent an arrow coming out of the page. So that's something that we'll see a lot more of when we look at electromagnetism next year. So this force of gravity for this picture here is going into the page. That means that the force of gravity is perpendicular at all times to my velocity, because here it's into the page, that's a right angle. Here it's into the page, that's a right angle. Here it's into the page, velocity will go this way, but it's still going into the page. And here's my velocity over this way. So at all these points, the magnitude of gravity, or the direction of gravity, is perpendicular to the direction of the velocity. Even though the direction is changing, gravity is still perpendicular. So there's our principle 2 that is being correct. And this is why it's called uniform circular motion. If an object was moving in vertical motion, the gravity would be assisting and stopping or hindering, its motion. So here is a picture of vertical circular motion. So we can see here at the sideward points. Imagine this is me sort of spinning my keys around a circle as I, stand there in class. We can see here that the tension force on the string is acting inwards, and gravity is acting downwards. It's acting at right angles. But here we can see this is right angle clockwise, or this is right angle counterclockwise from the tension. So even that is different from each other. But here at the top, we can see gravity and tension acts the same direction. That's kind of a problem. But here, gravity and tension acts different directions. Tension inwards and gravity in the other words. And notice how much this force is so much bigger than this force, because it has this extra pull outwards. These two are the same, different direction but same magnitude, and this one up here is so much less because it now has this gravity force that is also working to turn it around. It's acting to assist its center seeking. This plus this should give us the same length as that, and this plus this would also give us the same length as that, because this would be taken away from here. So this vertical motion, non-uniform. Horizontal motion, uniform. Okay, so we've just got to keep that in mind. And this could be a valid sort of thing for a student experiment if you wanted to puzzle your way through it. It is a bit harder though to get decent data on this sort of thing. So let's talk about the word speed. We have a moving object, which means we have to consider what speed would be in this case. Now, the average speed of an object is distance travelled divided by time. Speed equals distance over time. That's still true, because remember, speed is a scalar. It's not a vector. So even though our object is moving in a circle, that doesn't matter. We've still got our speed. We have, though, a little bit of useful theory in regards to the distance, and that's because we're dealing with a circle. And so instead of writing it with d, we can write it like this. 2 pi r divided by t. Now the capital T is because we've changed from time to something called the period, which is, we'll get to that on the next slide, but it's just a specific value of time. Okay? The thing is, the formula booklet doesn't write this, or even speed equals 2 pi r over t. The formula booklet writes this. Tangential velocity equals 2 pi r over t. And the good news is that's actually true. Okay, so in this case, tangential velocity, not the velocity of how fast it goes around the circle, but how fast it moves at that point in time. Let me just draw that for a second. Circle. So this is my v, okay, and my v would be here, but the velocity of how fast it goes around the circle, so v equals tangent, we give it a new symbol called omega equals rotational speed. Now this is not in our syllabus, but it is important for us to understand the difference and why all the fine detail we went into linear motion we're kind of throwing out off the side here. And that's because rotating systems have a couple of different things going on. The linear stuff is not the same as the linear formulas won't work as easily in this situation. We have to do some transformations to it. Now, I'm not going to cover the transformations, it's not relevant to the syllabus, but I do want you to understand why we're using this v. This v represents tangential velocity. And if you think about this instead of being a circle as just being one long straight line, then v will always be the same magnitude and same direction. Okay? And t in this case period will just be the time it takes to cover the whole thing. It's just that this length here would equal 2 pi r to tell you how long it is, and that's what's happening here. Okay, so it is a little bit of a weird one, I do get that, but you just have to sort of take it on faith and then slowly work through until you get comfortable with the ideas and you see what's going on. Okay, let's talk about time then in this period. So when we deal with circular motion, there are two terms that will pop up to help you think about time. The first is period, and this is a fairly easy one, and the period is the time taken for one full circular motion. So the time it takes to go in one circle. Nice and easy. The second one is revolutions per minute, otherwise known as RPM, and if you have a look on your parents' car dash, you will see that there are two devices that go up and down. The first is speedometer, the second is your engine revs, so your RPM, and that tells you how many times per minute your engine is firing in lots of 1,000. Now, this just tells us how many full circles are done in 1 minute. Okay, revolutions per minute. Revolution means a circle. Per minute, how many per minute? While RPM, though, is technically a measure for speed, because it's talking about how fast it does, or how many things it does in a minute. Remember, speed is distance over time. Number of revolutions in a unit of time is technically a speed. I tend to think of it as a unit of time because I can convert it to a period much easier than I can convert it to a velocity. So, I'm going to show you how to convert RPM to period in this, and I'll show you the theory, and then I'll show you the simple rule for it. Now, the rule is not provided on the exam booklet, so it's worth understanding why we do this. So let's write down this word RPM. Revolutions per minute means revs per minute. Okay. And we want to try to convert this to a unit of time. If we have this number here, so if I have, say, e.g., let's do an example, 30 RPM, that's telling me that it will do 30 full revolutions in 60 seconds, equals 30 over 60. Okay, if I have it as 30 over 60, that means the time it takes to do one revolution, okay, and I need this in the per second, okay, is going to be 30 divided by 60. That means, or therefore that becomes 0.5 okay, revs in 1 second. Or, if we flip it, 2 seconds equals 1 revolution. And that bit there is the important bit. Because that 2 seconds for 1 revolution is defined as, is linked to period, because period, remember, is defined as the amount of time it takes to do 1 full revolution. Okay, I'm going to say that this will then tie to our period. Okay? And so the period in this case is 2 seconds. So how did we do that? And the working out is not terribly difficult, but I don't really want to stress about it too much. So this was 30 over 60 equals 1 divided by t, because I had to flip it over the other way. Or period t equals 60 over 30. Now, where did we get these two numbers from? The 60 was our time, and the 30 was the number of revs. Okay, so I'll get rid of that in the middle. If you want to turn an RPM into a period, okay? And you might actually get a question where you get told something like, oh, it completes 25 revolutions in 40 seconds. Well, you can use this general approximation. But if you're just given RPM, say it has an RPM of 5,000, you would do something like, okay, well, time is going to be equal to 60, and the RPM is 5,000, so that's going to be 5,000, and we could then work out the T, or the period, okay? So this is not something, this formula here is not something that will appear on your formula booklet, not least from the version I currently have. It may change sometime down the future, so it's worthwhile to actually memorize it. Now, I'm going to actually do the examples in the next video, as we've put a fair amount of theory into this one, because it's a topic where you can't really piecemeal it out. You've got to delve into it all in one go. So do take a look at the worked examples in the text, and then go on to have a look at the video on the explanations. So, in this video, we have done the following. We have identified differences between uniform and non-uniform circular motion. And we've seen examples and definitions of the physical properties of circular motion. Now, this third point, solving problems, we haven't done that. We will do that next video. Okay. So, in fact, let's cross that out, because we did not do that for this one. So if you can do these two things, you are successful from this video. We'll have a look at some problems next video. Okay, now there are some good questions for you to delve into just for this. There are a couple of simple identify and describes. Please have a look at questions 1 to 4 from the chapter 3.1. You can get that on the what's the word I'm looking for? Off your book, or you can get it from the eLearn. Please put those into the 2.4 space on the eLearn. They shouldn't take you too long. Thanks for listening, guys. Have a good night.